In this video, I'm going to go over the answers to Classwork 5. Part A says, in Chapter 4, we learned that if U, x1, x2 represents a set of preferences, any monotonic transformation of U represents the same preferences. To demonstrate, use R to draw the level curves U, 1, 2, 3, 4, 5 for the utility function U, x1, x2 equals x1 times x2. Then use R to draw the level curves U, 1, 4, 9, 16, 25 for the utility function V, x1, x2 is U squared, which is x1 squared times x2 squared. Why is the square a monotonic transformation in this case, but not in general? So the first thing you'll do is I'll pretend I'm in R and just write out the code here. But I would do, so to use R to draw the level curves for this utility function, the first thing is I'll write, so the level curve where the utility is 1 is going to be x1 times x2 equals 1. And then I'll solve for the y variable, whatever variable I'm putting on the y-axis, which will be x2 here. So see, I'll get x2 is 1 divided by x1. And then the utility, the level curve for the utility of 2, 3, 4, and 5 will just be x2 equals 2 over x1, x2 equals 3 over x1, all the way up to 5 over x1. So in R, what I can do is I'll follow the same template as in the workbook. I'll just initiate a empty plot using ggplot. Open parentheses, close parentheses just initiates a empty plot. And then I'll use stat underscore function, defining the function as this thing. It takes an x1 and it outputs 1 divided by x1. So that's my function. And I can give it a color. I can say color equals red, or whatever color you like. And then at the end, see, I'm running out of space here. I'll move it over. Maybe shrink it down a little bit. At the end, I'll have a plus to add another layer onto my plot. Then I'll do the same thing, but for the next level curve, which is 2 over x1, and then keep going with 3, 4, 5. And you can run that code to see what happens. All right. So next, the problem says, let's see, use R to draw the level curves U 1, 4, 9, 16, 25 for this utility function, V. So let me shrink down everything that I've done. Put that over here. Now we're working with V, which is x1 squared times x2 squared. And you can see this is the same thing as U squared from over here. So again, we're gonna draw the level curve for U is 1, or in this case, V is 1. 1 equals x1 squared times x2 squared. Solve for my y variable, and that'll be 1 over x1 squared is x2 squared. And I can take the whole thing and square root it to get x2 is square root 1 over square root x1 squared. And of course, this would simplify to being 1 over x1, which is the same thing as here. So we shouldn't be surprised that it leads to the same utility function. Sorry, the same indifference curves. So I'll just copy paste this. Our code is going to look a lot like this, but I'm going to have function that takes x1 and outputs 1, let me write that out. So I want to output square root, that's the function in R to do square root of, let's see, what do we want? This should also be squared, right? No. Okay, that's just 1. So I'm doing squares here. It should be 1 divided by the square root of x1 squared. And then have the color, move this over. Okay. And then same idea down here. Instead of saying square root 1, we'll do square root of 4. And then a new color. And then square root 9, 16, 25. When you run this code, and when you run this code, you should see they create the same indifference curves, because this is a monotonic transformation. V is a monotonic transformation of U. And the last part of the question asks, why is it a monotonic transformation? In this case, but not in general. So in general, the square would not be, let me just delete all of this to see. So we learned that a monotonic transformation is something like this. We have bundles A, B, and C, and U1 and U2. Let's say bundles A, B, and C have utility, say -5, 0, and then 5, so we like C the most. And then a monotonic transformation is something like 2 times U1, or 2 times U1 plus 3. Let's just take 2 times U1. That would be -10, 0, and 10. It preserves the same ordering of the bundles. In this case, take U2 being U1 squared. Then we'd get 25, 0, and 25. So in general, the square function is not a monotonic transformation because it doesn't preserve the same order. Now we like A and B the same amount, A and C the same amount and B less. So in general, the square is not a monotonic transformation. But the key is the domain of U. Consider, domain of U. U is x1 times x2. x1 and x2 are the amounts of good 1 and good 2 that are in each bundle. x1 has to be greater than or equal to 0, and x2 is also greater than or equal to 0. So U is the product of these things. U has to be greater than or equal to 0. So if we just consider utilities that are greater than or equal to 0, so for instance 0, 1, and 2, and then we take the square of those things, now we have 0, 1, and 4. Now the square is a monotonic transformation. It does preserve the same ordering. And we can verify that. We discussed that all monotonic transformations have the property that the derivative is always positive. What's the derivative of the square? That would be something like this. So that would be 2 times U1. And when U1 is always greater than or equal to 0, then we have like a function like this, always positive. All right, let's go on to part B. It says, take the utility function U x1, x2 is x1 plus x2. use R to draw some of the level curves. This utility function represents perfect substitutes, perfect complements, or one bad, one good. So we can do exactly the same thing as before. Let's let u be 1. 1 equals x1 plus x2. Solve for our y variable. Then we get x2 is 1 minus x1. And I'll use, my R code is gone. I don't want to back up so far. So I'll copy it out again. So initiate a blank plot with ggplot. And then use stat function with fun equals a function that takes an x1, and I want to do this with it. Say 1 minus x1 and give it a color. Color equals red. And then I'll draw a level, so that's the level curve for utility of 1. I can draw the level curve for utility of 2, make it a different color, orange, and onward. You just replace it with 3, 4, 5, whatever you want. So that's how to draw some level curves for this utility function. When you draw these level curves, you're gonna get, so think about this. You should expect to get, this is y equals 1 minus x. Our slope is -1. Our y-intercept is 1 in this case. So we're going to get a utility function like, or the indifference curves are going to look like this. So that should remind you of this perfect substitutes example. When we had, our example was butter and margarine, we're indifferent between getting, 1 cup of margarine and no butter, 1 cup of butter and no margarine, or getting half a cup of butter and half a cup of margarine. We just want to make a batch of cookies. It doesn't matter how much margarine or butter we're using, we just want a cup of it. So that's perfect substitutes. All right, let's go on to part C. Part C says, we learned that the marginal rate of substitution measures the slope of an indifference curve, and it can be interpreted as the